Okay, good afternoon. We'll get started in a minute. All right. So good afternoon again. Let's get started. So in Wednesday last week, we started a discussion on the systems for facilities planning, and we talk about different type of systems that are part of the design of the facility. And we stopped our discussion when we got to the atmospheric systems, specifically the design of an HVAC system for a facility. And here's where we stop in terms of the design of a HVAC system. Yeah, facing some issues with my laptop today. Here we go. Okay, so we talk about the purpose of heating, ventilation, and air conditioning, and that was to control the temperature, humidity, and cleanliness of the environment within the facility. And the input required by an HVAC expert to design an HVAC system includes the facility layout and the construction specification. So the facilities planning should be able to provide the HVAC expert with this input, facility layout and the construction specifications, and should understand how the HVAC expert translate this input into the HVAC requirements. So as part of our discussion, we were trying to compute the heat loss for a facility, so we can compute and provide that information to the actual designer of the system. And we talk about the requirement and how to compute that information using this formula. The heating requirement for facility is referred to as the heat loss and is calculated using this formula. And we discuss an example in which we computed each one of these elements. So the heat loss in terms of the floor, or through the floor, through the roof, through the glass windows, through the doors, the walls, and heat loss through to infiltration. It was very simple. We use these coefficients that are based on the location of the facility. Those coefficients U, coefficient of transmission of the facility component. And then we also needed the information about the temperature inside and outside the facility. So in this case, TI represents the temperature inside the facility, and TO, the temperature outside the facility. And finally, we need the area of the component. So if we were looking at the floors, we will compute the area for the floor. If we needed the roof, compute the area for the roof, and the windows, doors, and so on. So we went through an example, and then we also talk about the air conditioning requirement for a facility or the cooling load. And this formula is quite similar to the heat loss formula, but we have some additional components here. So they are listed in this first side of the figure. This area, including the floor, the roof, the glass window, the cooling load due to the doors, the walls, the ventilation, the solar radiation, the lighting, and also because of the personnel that is inside the facility. And we have some additional formulas in addition to the cooling load for the facility component. Formula that takes also into account the area and the coefficient of transmission of the facility component and the temperatures. We also have some additional information or some additional formulas to compute the cooling load from solar radiation and also for the lights that we have inside the facility. And the cooling due to load from personnel may be calculated using QP. And that's going to be determined according to the number of people that you have inside the facility and according to the type of work that is performed by these people. So this is the first example. In this one, we were interested in calculating the heat loss. So we went through this example. We were able to complete the exercise without major issues. As I mentioned in the previous lecture, the challenge here is to identify the area for each one of the components. So for the Q floor, we were able to get the area 250 times 100. And then the U factor is given for Chicago, Illinois. So for the floor, that was 0.81. And then the temperature difference was 70 degrees inside that were needed inside the facility. And the temperature outside was zero Fahrenheit degrees. So any questions about this one? Okay, quite simple. The next example, and this is the last thing we did, we were trying to compute the cooling load for the facility given this information. So we're getting the information from example 1 for the same facility, and we were given some additional information, and we were asked to complete or to compute the cooling load for the facility. So we have information about the front of the facility faces west, and all windows and doors have awnings. The lining within the facility consists of 575 fluorescent luminaries, each containing two 60-watt lamps. And within the facility, 75 men performing light work and 50 women performing light work will be employed. The outside design temperature is 90 degrees Fahrenheit, and the inside design temperature is 78 degrees Fahrenheit. So following the formulas, we were able to compute the Q factors for the first 5, floor, roof, and for the doors, for the windows. And now we have to compute the rest of them. So we're going to continue, and the next one that we are going to compute is the Q for the ventilation. So for the ventilation, we have to take into account the walls, the area of the walls, and the area of the roof. So it's the whole area for the 4 walls in this case, and the area of the roof. So let's start with the area of the roof. This is 250 times 100 plus the area of the walls. We have 4 walls that are if you get the area of the, if 250, let's go back. 250 by 18. So this is two walls with an area of 4,500 and two walls with an area of 1,800. So this is the area of the roof. This is the area of two of the walls. And this is the area of two of the walls. And all that multiplied by the U factor. Times the difference between the temperatures. So this is 97 degrees Fahrenheit minus 78 degrees Fahrenheit. And this QB equals 1.43 10 to the 5 BTUs an hour. And then for the solar, we started that computation for the heat absorption factor for the west side of the facility in Chicago is 100 BTUs an hour square. And for the east side is 75 BTUs an hour. So the shade factor on is are 0.3. So using that information, we were able to compute that factor, the solar radiation factor. So we have two more to go. The lightning factor. So for the lightning, we have this this formula, QL for incandescent. We're gonna use the incandescent wattage and then multiply by this factor. And for the QL fluorescent, we have the fluorescent wattage and multiplied by 4.25 BTUs hour watts. So in this case, let's see what type of lining we have. We have fluorescent luminaries, stated here, 575 luminaries, each containing two 60-watt lamps. So we're going to use that information for fluorescent lights. So let me make that clear. Fluorescent. So again, going back here, we get the wattage and then multiply by this. So we have 575, which is the 575 fluorescent luminaries, each one of them containing 60-watt lamps, two 60 watts. So this is 2 times 60 watts. And then multiply by the factor 425 BTU hours Yes. So 575 fluorescent luminaries, each containing two 60-watt lamps. So that's the total illumination in the facility. The what? This one? Yes, yes, yes. So that's coming from here. Good question. So this is going to be equal to 2.93 10 to the 5 BTUs an hour. And then finally, we have the Q for the personnel. And going back to the formulas, the cooling flow from personnel may be calculated by determining the QP number of men and women performing light and heavy work and multiplying that times the heat gain factors given in this table. So we need to find out how many we have in terms of men and women, and also the type of work that they're going to be performing. So in the statement, we have 75 men performing light work and 50 women performing light work. So we're going to find those factors here for light work. It's 800 for men and 700 for women. So using that information, we can compute this QP factor. So we have 75 men times 800 BTUs an hour. And we have 50 women with a factor of 700 BTUs an hour. And this is 0.95 times 10 to the 5th BTUs an hour. So now we have all the coefficients for this facility. So the cooling load for this facility is going to be equal to the summation of those factors, all those factors. So here's the statement. So the cooling load or the conditioning requirement is going to be equal to this summation. So QC will be equal to 3.85 10 to the 5 plus 0.95 10 to the 5 plus 0.06 10 to the 5 plus 0.02 10 to the 5 plus 0.88 10 to the 5 plus 1.43 10 to the 5 plus 0.16 10 to the 5 2.93 5 plus 0.95 10 to the 5, and this gives us a cooling load of 11.23 10 to the 5 BTUs an hour. So for the facility that we are trying to design, this will be the cooling load necessary to keep the temperature of what was the desired temperature, 78 degrees. You need a cooling load of 11.23 times 10 to the 5 BTUs an hour. So if you were to design, or if the HVAC experts were to design a air conditioning for this facility, this is the capacity that their system must have. For this temperature, obviously. So if you want to have a temperature of 78 degrees inside the facility. Any questions? So that's the last topic for this lecture. Today we're gonna continue our discussion on the next set of slides. So the question is, if the temperature difference is negative, should we keep the total BTUs an hour as a negative result? It should not be negative. Maybe if you look at the formulas, so when we are looking at the heating requirement, we are doing Ti minus T out. So T inside minus T outside. And T inside, since you are trying to define the heat requirement, T inside will be higher than T outside for the heating component. So you want to keep a warm temperature inside the facility, so that temperature should be higher than the outside temperature. So Ti minus T0 for the heating requirement. And then for the cooling requirement is the opposite. We have TO, or the T outside, minus the T inside. So when you're trying to cool, that means that the temperature outside should be higher than the inside, or you're planning, or you're designing for a system that will have a higher temperature outside than inside. So in that case, the outside temperature will be higher than the inside temperature, and the difference will be positive. So in the assignment, the outside temperature is 98 and the inside. So it would depend on what you're designing for. So if it is outside 98 and the inside temperature you want is inside 78 degrees, then you're trying to design for a cooling system. And the difference will be TO minus TI, and that will be a positive number. So for the coefficients, those will be given. So let's go to the next slide. So in this lecture, we are going to complete this material. We're going to learn how to design for other type of systems. So this also tied to objective number 4, be able to design layouts incorporating products, process, and personal requirements. And today we're going to focus on those two, electrical and lighting systems and life safety systems. So in terms of the learning objectives, we want to provide an overview of how the system's elements impact the overall process of facilities planning. We want to provide an understanding of the various systems elements within the facility. So remember not to prepare the facilities planning to design a structure of heating, ventilation, or an air conditioner or other systems. What we want is you have an idea and be aware of the design requirements for your facility. So today we're gonna look at the electrical and lighting systems. And the facilities planning responsibility is to specify what level of service is required and where it is required. The power company needs the electrical load requirement for a facility before construction begins. So it requires the facilities planner to have a good preliminary estimate. So if you're going to construct a facility, and depending on the type of processes that you're going to have inside the facility or the type of machinery that you're going to have inside the facility, also the type of lining that you're going to have inside the facility, all those things must be taken into consideration. So in this case, we're going to be focusing on the electrical and lining systems. The facilities planners must ensure that major load requirements, both present and future, are included in the design data. And using this information, the design engineer can adequately size main fixture transformers, feeders, panel boards, and circuits. So table 1 has an average load requirement for the different building types. For example, for plants, about 20 watts per feet square. Office buildings, about 15 watts per feet square. Hospital requires much more than that, 3,000 watts per bed. Schools, about 3 to 7 watts per feet square. In shopping centers, between 3 and 10 watts per feet square. Facilities lining should not be planned by the same person planning the electrical services, because illumination should be custom designed for the areas within the facility. Specifically, if you're going to have different type of operations being performed. Some of them will require some certain level of lighting, and some other areas will require a different requirement for the lighting. So lighting system may be designed using the following 8-step procedure. So first, we're going to determine the level of illumination that is needed for the facility, and that will depend on the type of operation that you're going to be performing inside the facility. So the minimum level of illumination for specific tasks are given in table 2. So I'm going to show that in a minute. When selecting the level of illumination for a particular workstation, the following criteria must be considered. Again, you have to take into account the nature of the task, the amount of reflectivity of the workstation, components, and surrounding area. So if you're going to have, I don't know, some lights hanging, there's a reflection component with the roof and also with the walls. The current level of natural or general lighting, the need of natural illumination, and also the average worker's age and visual acuity. So I don't know if you can see this from there, but this is a table from your textbook. And what it does is it shows the different tasks that are typically performed in a manufacturing facility. And based on those tasks, the minimum level of illumination in terms of foot candles for that activity. So for example, if we have assembly operations, it could be rough, easy scene, rough, difficult scene, medium, fine, extra fine. And depending on those different levels of activities, you can determine the level of illumination that is needed. If you're doing inspection, if you're working on a machine shop, depending on the type of work that is performed, for material handling, for offices, paint shops, welding, and so on. So this is information that is already tabulated. You will know what is the minimum illumination according to the different type of tasks that you're going to be performing in the facility. And then using that information, we can continue. So step 2 is to determine the room cavity ratio, or RZR. The RZR is an index of the shape of a room to be lighted. So the higher and narrower a room, the larger the RCR, and the more illumination needed to achieve the required level of lighting. The RCR may be calculated using this equation. So as you can see, the area of the room is taken into account here, the room weight, length, and width. And we also take into account the height from the working surface to the luminaries, and also the summation of those length and width for computing this ratio. Step 3 is to determine the ceiling cavity ratio. So if the luminaries are ceiling mounted, like this ones, you see, those are ceiling mounted, they are not hanging, or recessed into the ceiling, then the reflective property of the ceiling will not be impacted by the luminaries mounting height. So the CCR need not be considered. So in that case, we're gonna say, okay, we don't need the CCR because these lights are ceiling mounted. In the case that they are not ceiling mounted, that they're hanging, we need to compute the CCR ratio. The greater the distance from the luminaries to the ceiling, the greater will be the CCR and the reduction in ceiling reflectance. The CCR may be calculated using this equation. So again, we need the height from the luminaries to the ceiling. We need the RCR that was computed in step 2. And then we need the height from the working surface to the luminaries. So in this case, that will be, if this is my working surface, the height from here to where the luminaries are located. Step 4 is to determine the wall reflection, or WR, and the effective ceiling reflectance, ECR. The WR and a base ceiling reflectance, BCR, value can be obtained from table 3. So that's table 3 right here. And you can see in table 3 gives us the approximate reflectance for wall and ceiling finishes. So basically looking at the materials that are used for the finishes of the walls and the ceilings. So it could be, for example, white paint or light color paint. The approximate reflectance is going to be about 80%. If it is an aluminum paint or stainless steel and polished aluminum, it's about 65. Medium color paint, 50%. Brick, cement, and concrete, 35. Dark color paint, 10%, and black paint, only 5. Okay, so those reflectance ceiling finishes are relevant. It's going to impact also the type of luminary that you're going to need for your facility. So using those ratios, then we can compute the percentage effective ceiling reflectance, or ECR, for various combinations of these ceiling cavity ratios, wall reflectance, and base ceiling reflectance. So if you have the BCR, the base ceiling resistance, base ceiling reflectance, if you know that number, you look at that number here at the top, and then you look at the wall reflectance, depending on what level you end up with. You have to look at those values here, and then you look at CCR on this column, and then the combination will give you that value of this ECR, or the effective ceiling reflectance. So for example, for a BCR of 80, a WR of 50, and a CCR of 1.5, we're gonna get an ECR of 62. Yes, so in order to get that effective ceiling reflectance, ECR, we have to use the value for BCR, or the base ceiling reflectance, the wall reflection, and the CCR. So using a combination of these 3 values, you can find the ECR value inside the table. So the example I was given is for VCR of 80, wall reflectant of 50, and in CCR of 1.5, the ECR value will be 62. That's where all of these three values intersect. You will see this in an example. Step 5 is to determine the coefficient of utilization. The coefficient of utilization is the ratio of lumen reaching the work plane to those emitted by the lamp. It is a function of the luminaries used, the RCR, the WR, and the ECR. The coefficient of utilization for standard luminaries is given in table 5. So again, we're going to use the values of the ECR, the wall reflection, and the RCR to get this information. We also need the type of luminary and the spacing. So 5 pieces of information to find the right number. And then step 6 is to determine the light loss factor, or LLF. The two most significant light loss factors are lamp lumen depreciation and luminary dirt depreciation. So we have to take that into account. The lamp lumen depreciation is the gradual reduction in lumen output over the life of the lamp. Typically, lamp lumen depreciation factors are expressed as the ratio of the lumen output of the lamp at 70% of the rated life to the initial value. The lumen outputs for various lamps given in table 6 include the lamp lumen depreciation. Therefore, no additional consideration is needed. Luminary dirt depreciation is the light loss associated with the conditions under which the luminary operates. So if, for example, if you are in a machine shop, you will expect those lights to get some dust and get affected by that. So the luminary dirt depreciation varies with conditions and the length of time between the cleanings. So this is table 6. Here we have the lamp type, filament, high intensity discharge, or fluorescent. We also have the capacity in terms of watts and the lamp output at 70% of rated light. So filament for 100 watts, the lamp output at 70% is going to be 1600. For fluorescent, 110 watts, the lamp output at 70% of rated life is 7500. The lamp luminary dirt depreciation factors. So again, now taking into account the dirt condition, we have 4 different scenarios in this table. So for example, for clean offices, light assembly, or inspection. So in an environment like this one, you don't see a lot of dust, it's clean. We will use this piece of the table to compute for the lining. But if you are like in the very dirty foundry or heavy machining scenario or application, then the factors that will apply to you in terms of finding the lighting will be the ones on the right of the table. And again, we're going to use information about the environment or dirt condition of the facility. And also we need information about the cleaning or the period between cleanings. So are you going to be cleaning these lights every 24 months, 36 months, and so on. And then once we get all that information, see a lot of work there, we use that data to compute the number of lamps that are needed for the facility. So equation 3 is used to calculate the number of lamps, and equation 4 to calculate the number of luminaries. So the number of lamps include the required level of illumination. So that was computed or that was found on step 1. So 100 foot candles, for example. The area to be lit. And then we need the CU and LIF factors and the lamp output at 70% of rated light. If you find the number of lamps, then finding the number of luminaries is simple. You have to take into account the lamps per luminary, and you divide the number of lamps by the lamps per luminary. So let's try to work with this example. We are working on designing a machine shop with an area of 100 foot and 40 foot by 40, and with a 30 feet ceiling will be illuminated for automatic machining and rough grinding. So this is telling us about the type of facility that we're going to be working on. Uniform lighting is required throughout the machine shop. If the luminaries are to be ceiling mounted, all ceiling and walls are to be painted white, and all luminaries are to be cleaned every 24 months. So the question is, what lighting should be specified for this facility? So let's go step by step. So the first step is to determine the level of illumination. And we have the description right here. It's an automatic machining and rough grinding facility. So if we go to table 2 on this slide, we can find that automatic machining and rough grinding. If we can find that. Yep. So let me highlight this. Illumination required for that is 100 foot candle. Okay, so let's go back here. So this will be 100 foot candles. Level is required. Step 2 is to determine the room cavity ratio. And for this, we are going to assume that all working surfaces are 3 feet from the floor, which is typical, like a table, or a little bit higher than those tables. We are going to assume that 3 feet, yes. in the exam, I will be very specific. So I will provide the information that you need. Okay, but if it's not listed, then you can assume 3 feet. So the RCR is right here. So you're going to use this formula to determine the room cavity ratio. So we need the height from the working surface to the luminaries, and the room length, the room width, the room length, and the room width again. So RCR is going to be equal to 5, which is part of the equation, times 13 feet, which is the ceiling height, minus the height for the working stations, times 100 feet plus 40 feet divided by 100 feet times 40 feet. And this is equal to 1.75. So our RCR is 1.75. Number 3 is to determine the ceiling cavity ratio, or the CCR. In this case, we have ceiling mounted lights. So as stated here, if the luminaries are ceiling mounted, then the reflective property of the ceiling will not be impacted. So the CCR need not to be considered. So that's the case for this problem. We determine the ceiling cavity ratio So in this case, the CCR need not to be considered. As luminaries are ceiling mounted. Okay, so the next steps is to determine the wall reflection and effective ceiling reflectance. So for determine the wall reflection and the effective ceiling reflectance. According to table 3, So let's look at table 3. Okay, so we have so the problem says that the walls are to be painted white and all luminaries are to be cleaned every 24 months. So from the problem we get this, the white paint. So white paint. So the approximate reflectance is 80%. So the white reflection and the base ceiling reflectance are obtained from table 3. And for both, the value is going to be 80% because we are using the white paint. So our BCR and WR are going to be 80%. So if the luminaries are to be suspended, then the ECR is determined from the CCR, WR, and BCR using table 4. So if the luminaries were suspended, which is not the case for this problem, but if they were suspended, then you will use the values for the BCR, WR, and the CCR to compute this ECR. But that's not the case for this problem. In this problem, the luminaries are ceiling mounted. So the ECR is equal to the BCR. So that means that WR, BCR in this problem is also equal to the ECR for example 1. So going back to the example, we found that WR and BCR are 80%. And because the luminaries are to be ceiling mounted, the ECR is also 80%. So we have RCR 1.75, we have WR equals 80%. We have the BCR also 80%. And the ECR also equal to 80%. Step 5 is to determine the coefficient of utilization. So we are going to use table 5. To find this coefficient of utilization. So we need some additional information. So the luminaires are to be ceiling mounted. Okay, so we know that we have fluorescent lamps. So if fluorescent lamps in uncover fixtures are to be utilized, the CR may be interpolated in table 5 as being between 0.88 and 0.78. A coefficient of utilization of 0.8 will be utilized. Okay, so you're going to go back to table 5. So our ECR is 80%. So ECR 80%. Our wall reflectance is also 80%. And the RCR is 1.75. So our RCR depends on what type of luminary we're using. So if we use fluorescent lamps in uncovered fixtures, our RCR is going to be between 1 and 2 because it's 1.75. If I remember correctly. Yes, 1.75. So we know the value will be between 1 and 2. And to get the exact number, we're going to have to interpolate. For the purpose of this class, we want a value between these two, right? So it is going to be closer to 2, that is going to be to 1. So if you interpolate, that would be 0.80, which is what we are stating here. So the coefficient of utilization is 0.8. Okay, so we are getting close to the end. Step 6 is to determine the light loss factor. Can I move to the next slide or just you fine? Okay. So let's go to the next slide because I need more space. So step 6 is to determine the light loss factor. And for fluorescent lights with uncovered fixtures in a medium dirty environment, that are cleaned every 24 months. A lamp luminary dirt depreciation factor of 0.85 may be obtained from table 7. Okay, so the light loss factor for fluorescent lights with uncovered fixtures in a medium dirty environment that are cleaned every 24 months, lamp luminary dirt depreciation factor of 0.85 may be obtained from table 7. Okay, so we have the information. These are going to be cleaned every 24 months. And this is a machine shop with rough grinding and automatic machining. So we can assume that there's going to be some dirt there, medium dirty environment. That's what we're assuming for this environment. So if I go to table 7, I'm referring to this table. And from here, I'm looking at this medium processing and machining for cleaning every 24 months for fluorescent lamps with uncovered fixtures. So that value is going to be 0.85. Medium processing, light machining, fluorescent lamps with uncovered fixtures, and with cleanings every 24 months, where everything intersects is 0.85. So that would be the lamp luminary dirt depreciation factor. And now I have all the information that is needed to compute the number of lamps. So this is going to be LLF equals 0.85. So to calculate the number of lamps, we have this equation: required level of illumination, the area to be lit, the coefficient of utilization, the factor that we just computed, and the lab output at 70% of rated light. So 7, calculate the number of lamps. Number of lamps equals, so this is 100-foot candles. The area is 100 by 40. And the coefficients are 0.8, 0.85, and 3,300. And this is going to be equal to 179 lamps that are needed for this facility. That'll work. So if I were to ask you something like this in the exam, I would have to pick some of the coefficients, might give you the rest of the information, because computing this whole thing will take you 30 minutes. So understand the process, understand where to get the information, and I can definitely can ask you a question in which you can complete some of the steps of the process. Questions? Okay. So yeah, I'm gonna stop here. We're going to go over life safety systems on Wednesday. And I think that's all you needed to complete the assignment. So you should be good to go to complete the problems for the assignment. And then I'll see you on Wednesday. We'll complete this lecture and we will continue our discussion. Okay. Have a good rest of the afternoon.